Tonight, we're going to drift back, not just a few centuries, but 66 million years, into a world that feels both familiar and impossibly distant. A world of warm seas, broad river plains, and deep green forests where giant reptiles moved like living weather across the land. And then, almost in an instant, in geological terms, everything changes. This is the story of the great turning point at the boundary between the Cretaceous and the Paleogene. The layer of clay so thin you could miss it, yet so heavy with meaning that it rewrote the history of life. It's a story pieced together from stone, ash, chemistry, and fossils, and it's still being refined as new evidence rises to the surface. So let your thoughts soften. Imagine the hush of ancient oceans, the slow settling of sediment through quiet water. And as we go, remember, this isn't a tale of one single moment. It's a woven tapestry of causes, consequences, and clues. As we understand it today, imagine the late Cretaceous not as a single postcard moment, but as a whole living season that lasts for millions of years. A long, slow afternoon in Earth's memory, warm and bright, with a steady hum of life that has had plenty of time to fill every corner it can reach. If you could drift above the planet and look down through the soft veil of clouds, the first thing you might notice is water, not just oceans, though the oceans are vast and busy, but water spread into places where, in our time, you might find grasslands or cities or highways. Sea levels are high, and shallow seas push inward across continents, forming broad, gentle waterways that rise and fall with time. In some regions, coastlines are not fixed lines but wandering edges, moving, retreating, returning, patiently reshaping the map. And because the world is warm, those seas are often lively. Sunlight pours down into the surface layers, and microscopic organisms, plankton too small to see with the naked eye, float and multiply, feeding on light and chemistry, forming the base of food webs that stretch upward to creatures large enough to cast shadows like ships. Now, slowly, let your viewpoint lower, down from the global view, down through the atmosphere, down toward land. The continents are recognizable in their broad shapes, but not quite the same. The familiar puzzle pieces have not fully settled into their modern arrangement. Some land masses are closer, some farther. Between them, currents move heat around the planet in steady, complicated loops. The climate overall is warmer than what we're used to, and the poles, rather than being locked under permanent ice, can host forests in many places. There are seasons, especially in higher latitudes, and long days and long nights, but the world is not dominated by polar ice the way it is today. Picture a forest near a high-latitude coast. The air is cool compared with the tropics, but not frozen. The ground is soft with ancient soil and leaf litter. Conifers rise like tall, patient spires, and beneath them are ferns and shrubs and early flowering plants, their leaves catching the low angle of sun. Insects buzz, crawl, and shimmer. Small animals slip through undergrowth, cautious and quick. Somewhere, water moves, perhaps a slow stream, perhaps a marshy edge where reeds sway gently. Life is present in layers, canopy, understory, ground, and the hidden world beneath. Because in this time, the world is layered. Everything is layered. On the plains and river deltas, the landscape can open wide. Broad floodplains stitched together with channels that shift with each wet season. Rivers here are not confined by concrete banks. They wander, they carve, they deposit, They braid into multiple channels and then choose a new path when a storm season swells them. In the shallow bends and oxbow lakes, sediment settles like a slow snowfall of silt. If you stand very still in such a place, if you can imagine standing there without being seen, you might hear the most soothing kind of ancient sound. Wind moving through leaves, the soft chatter of insects, distant calls that are unfamiliar but still clearly alive, and the faint hush of water. The air carries scents too, even if the exact notes would be strange to us. Damp soil, resin from conifers, crushed fern, and the green, slightly sweet breath of flowering plants. Because flowering plants, angiosperms, have become increasingly common by this point, and they're changing the texture of ecosystems. They introduce new kinds of leaves, new growth habits, and importantly, new relationships with pollinators. This is a world in which insects and plants are learning each other deeply, shaping each other over time, refining their quiet exchanges. In many places, the vegetation is not a single kind of forest, it's a patchwork. Wooded areas, fern prairies, open plains, and wetland margins. Fires can happen in dry seasons, storms can flatten stands of trees, and rivers can rewrite the ground. The result is variety, and variety makes room for many forms of life. Now, very gently, let your mind step closer to the animals that make this era famous, but try to see them not as movie monsters, not as roaring caricatures, but as living creatures doing ordinary things in their own time. A large herbivore moves through the edge of a forest, not sprinting, not fighting, but feeding. It lowers its head to crop plants, then lifts again to scan and breathe. The motion is slow, economical, practiced. It doesn't need to rush. It has spent its life learning the landscape, whether new growth appears after flooding, whether tender leaves sprout after a disturbance, where water remains even when the season grows drier. In some regions, you might see hadrosaurs, duck-billed dinosaurs, moving in groups. They are not identical. Different species occupy different habitats, and each has its own shape, its own crest, or head profile. You can imagine the gentle rhythm of a herd, the shuffling, the occasional pause, the subtle communication through body position and sound. Their footsteps compress the earth. Their movement stirs insects from the plants. In their wake, smaller animals follow, scavengers and opportunists, creatures that live by noticing what the giants disturb. In other places, you might encounter ceratopsians, horned dinosaurs, built like living tanks of muscle and bone, with broad frills and faces that look almost ceremonial. Yet their lives are practical, feeding, migrating, nesting, guarding the young. You can imagine the way they would move through brush, strong shoulders pushing aside vegetation, beaks clipping tough stems, lungs drawing in warm air. And then there are the armored ones, ankylosaurs, low and heavy, their bodies protected with bony plates. They move like ancient hills that learned how to walk. Their tails in some forms end in a club of bone, an instrument that could be used for defense, yes, but which also simply exists as part of their anatomy, part of how evolution sculpted them over time. Somewhere farther off, in the open, there might be sauropods in the regions where they remain, long-necked giants browsing high vegetation. The image is almost dreamlike, slow, enormous bodies moving with calm inevitability, necks sweeping through foliage like cranes. Not everywhere has sauropods at this late stage, and their presence depends on geography and time, but where they exist, they are part of the skyline. Predators live here too, of course. but try to imagine them the way you might imagine a lion or a wolf in the modern world. Dangerous, yes, but not constantly violent. Predators spend much of their time conserving energy, observing, waiting, moving with purpose rather than frenzy. A large theropod, perhaps a tyrannosaur in certain northern regions, would be an animal of muscle, senses, and decisions. It might travel along the edge of a river, using the waterway as a corridor. It would smell the air, notice tracks in mud, listen for distant commotion. It would not roar for no reason. It would exist within the economy of energy, when to move, when to rest, when to approach, when to avoid. And it would not be alone in the predatory niche. Smaller theropods hunt smaller prey. Some may be feathered, bird-like in outline, quick and precise. Some might climb or ambush. The predatory world is as varied as the herbivores, because variety is the rule here, not the exception. Above all of this, the skies are busy. Birds exist already, and they are diversifying. Some are shorebirds and swimmers, some are forest dwellers. And alongside them are pterosaurs, flying reptiles, some small, some enormous, gliding on wide wings across coastlines and inland seas. The biggest pterosaurs would have been among the largest animals ever to fly. And if you imagine one passing overhead, do it slowly. A shadow crossing sunlit ground, a quiet shift in the air, a creature riding currents with the calm confidence of something adapted to the sky. Near the coasts and in the shallow seas, life takes on a different shape. The shorelines are feeding grounds, nurseries, crossroads. Here you might find turtles in abundance, some large, some small, moving between land and water. Crocodilians and their relatives occupy rivers and wetlands, patient and still, eyes just above the surface, bodies suspended in water like living logs. These animals, well adapted to semi-aquatic life, are part of why freshwater environments can feel enduring through many changes. They are resilient, flexible, and good at surviving lean times. Further out, in the marine realm, the cast changes again. There are marine reptiles, mosasaurs, sleek and powerful, moving through the ocean with a predator's ease. There are plesiosaurs in some areas and times, with their own eerie grace. There are sharks and bony fish of countless kinds. And in the open water, the invisible engines of life, plankton, continue their endless drift. And then there are the shelled creatures, ammonites in many forms, coiled like living spirals, drifting and swimming and feeding in the seas. On the seafloor, reefs are not always the coral reefs we think of today. In many places, other organisms contribute to reef-like structures. Life builds structures. Life makes homes. Life becomes habitat for more life. It's easy from a distance to imagine the late Cretaceous as stable. It lasted so long. It produced so much diversity. It feels in the mind like a complete world. But the truth is gentler and more interesting. Earth is never perfectly stable, not even in its calmest eras. Change is always happening, sometimes slowly, sometimes in pulses. Like the planet is breathing. Sea levels shift over time. Climate patterns wobble. Ecosystems adapt. Species appear and vanish. The late Cretaceous is not a single day. It is a long chapter with many pages. In some places, the environment is lush and dependable. In others, it is seasonal and demanding. A floodplain might be generous during wet months and then more difficult during dry ones. A coastal ecosystem might shift as the sea advances or retreats. A forest might change composition as new plants spread and older ones recede. And while dinosaurs remain dominant on land, they are not a monolith. They are many different lineages with many different strategies. Some mature quickly, some more slowly. Some lay large clutches. Some invest differently. Some are specialized. Some are generalists. And all of them live inside food webs that depend ultimately on plants and plankton, on photosynthesis, on sunlight. If you want to make this feel even more real, imagine the ordinary details. A nesting ground in a sandy area, where eggs are buried or placed carefully, and adults guard or return. The air is warm. The sand holds heat. Small animals, perhaps lizards, early mammals, birds, skitter at the edges, looking for opportunities, always alert for danger. A thunderstorm builds in the afternoon heat. The sky darkens, not with catastrophe, but with weather. Wind stirs leaves. The smell of rain rises from the soil before the first drops fall. Then, heavy rain. Rivers swell. The landscape drinks. Afterward, everything glistens. Insects emerge. Plants straighten. The world resumes its slow, persistent growth. At night, the sounds change. Some animals quiet down. Others become active. The stars overhead are sharp and ancient. The moonlight, when the moon is up, turns water into a pale ribbon. Somewhere in the distance, a call echoes. Not a familiar bird call, not a familiar mammal sound, but something that still carries the same emotional information. Presence, warning, contact, the simple fact of being alive. And in that darkness, small mammals move. It's important to remember them because they are there, often tiny, often overlooked. They are not yet the dominant large animals of the land, but they have their niches. Burrowers, climbers, insect eaters, omnivores. They live in the margins and in the shadows, where smallness is a kind of safety. They are part of the quiet future, waiting. Now, when we speak about the end of the dinosaurs, it can sound like everything was already doomed, like the late Cretaceous was a stage set for tragedy. But it didn't feel doomed from the inside. From the inside, it felt like life. Generations lived and died without ever knowing the shape of the ending. Herds migrated along routes worn into memory. Forests returned after storms. Seas blossomed and thinned with the rhythm of seasons. Eggs hatched. Young grew. Predators hunted and missed and hunted again. The world continued. Still, there are hints of restlessness in the deep earth. If you could listen beneath the surface, you would hear that the planet's interior is never silent. Heat moves. Rock flows very slowly under immense pressure. Plates shift. Hotspots plume. Volcanoes form and erupt, not as isolated events, but as part of Earth's long internal conversation. And in the late Cretaceous, one of the most dramatic volcanic stories is unfolding in what we now call India. There, over spans of time, enormous lava flows erupt, flood basalts that spread across wide regions, stacking layer upon layer, building what will later be known as the Deccan Traps. These eruptions are not one continuous river of lava. They happen in episodes, pulses separated by quieter intervals. Each episode releases not only molten rock, but gases, carbon dioxide and sulfur compounds among them, that can influence climate and oceans. You don't need to imagine the eruptions as constant fireworks. It's more subtle than that when seen from the scale of ecosystems. A volcanic episode might mean hazier skies in certain regions, shifts in rainfall patterns, cooler or warmer intervals, changes in ocean acidity or oxygenation in some areas. The exact details are complex, and scientists still work to understand how these pulses interacted with life. But the essential idea is calm and clear. Volcanism can stress environments. It can nudge climates. It can make the world a bit less predictable. Not everywhere would feel it the same way. Some regions might barely notice. Others might experience more pronounced swings. The planet is large, and effects are distributed unevenly. But even uneven stresses can matter over time, especially for ecosystems that rely on steady patterns. Yet the late Cretaceous continues. Life continues. Inland seas still shimmer under sun. Coastal plains still host nesting grounds. Forests still breathe. The world remains abundant enough to support giants. And that, in a strange way, is what makes the end so striking in the record of stone. Because the world before the boundary is not a barren wasteland. It is a full, functioning planet with thriving systems. If you could hold a piece of late Cretaceous time in your hand, it wouldn't feel like an ending. It would feel like continuity, like a long inhale. Sediment settles quietly on seafloors. Tiny shells accumulate. Pollen drifts and lands and becomes part of mud that will harden into rock. Footprints press into soft ground and are filled by new silt and preserved by luck. Bones, when an animal dies in the right place, are buried gently, protected from scavengers, sealed away until deep time turns them into fossils. This is how we know the world existed the way it did. Not from a single perfect snapshot, but from countless fragments, tooth marks, eggshells, pollen grains, layers of volcanic ash, chemical signatures in rock, the changing shapes of tiny ocean fossils. Each clue is small, but together they let us imagine that warm afternoon world, the last quiet days of the Cretaceous, not as a dramatic prologue, but as a living present. So, let your mind rest there for a moment. A river plain under a golden sky, a distant herd moving slowly like a shadowed hill, the soft chorus of insects, a pterosaur gliding over water, the ocean beyond breathing with waves, the earth turning steadily, unaware of what is approaching, because Earth does not anticipate, Earth simply continues. And far above that calm continuity, beyond the blue of the sky, space remains what it has always been, wide, cold, filled with wandering stones that travel silent routes. Most of those stones pass by, but every once in a very long while, one does not. Try for a moment to picture the world as it was, full of green, full of motion. Then let your imagination lift gently upward, past the treetops, past the high clouds, past the thin edge of air where blue becomes black. Out there, nothing feels fast when you're watching from a distance. Objects move on paths that take years, decades, centuries. A stone can wander through space for an absurdly long time without ever touching anything at all. Most do. They pass Earth like quiet strangers in the night. But once in a great while, a path and a planet intersect. And the first clue that something is different is not the impact itself, because no one is there to witness it the way we witness things, but the suddenness. In the language of geology, sudden can still mean a day, an hour, even a minute. And what happens at the end of the Cretaceous is sudden. It begins as a bright point that grows impossibly quickly. An incoming body, likely an asteroid, hits the atmosphere at cosmic speed, so fast that the air in front of it compresses and heats. In the final seconds, the sky over what is now the Yucatan region becomes a place of furious light. Then the collision. In that moment, the boundary between space event and Earth event disappears. The energy released is not like any ordinary explosion, not like any volcanic eruption we've seen in human history, not even close. It's the conversion of tremendous kinetic energy into heat, shock, and motion, into a violence that happens faster than ecosystems can respond. Rock behaves differently under that kind of stress. Solid limestone and granite do not remain solid in the everyday sense. They shatter, they flow, they vaporize. Water flashes into steam. The ground itself becomes a temporary sea of debris and fire. A crater forms, an enormous one, excavated in a heartbeat, then modified in the next minutes as the earth rebounds, collapses, and settles into a new shape. The structure we call Chicxulub is not a simple hole, but a complex scar, a ringed crater roughly 180 kilometers across, buried partly beneath sediments and water, but still present, still readable, like a fingerprint pressed into stone. If you imagine standing nearby, only as an exercise of the mind, there would be no time to understand what you're seeing. The air would be brighter than day. The shock wave would arrive with a force that pulverizes, topples, strips. The heat would be immediate and overwhelming. Everything close to the impact site would be transformed in an instant. But the deeper story, the global story, is not only what happens near the crater, it's what happens to the sky. The impact doesn't just dig into Earth, it throws Earth upward. It launches an immense plume of vaporized rock, melted minerals, and dust high above the atmosphere. Material rises and expands like a mushrooming fountain, then spreads outward. Some of it escapes into space. Much of it does not. And when that material begins to fall back, it falls across a planet. This is one of the strangest features of the event, that a single moment in one region can leave a thin signature everywhere. Because what goes up in time comes down, and the Earth is round, and air circulates, and particles ride winds. So around the world, across continents, across sea floors, something settles out of the sky. In many places, the layer is almost disappointingly thin. Sometimes it's a narrow band of clay between other rocks. Sometimes it's a line in a cliff face, a subtle change in color. But within that line are clues that behave like a chorus. Many independent voices all pointing toward the same kind of event. There are tiny glassy droplets, spherules, formed from molten material that cooled while flying through air. There are minerals that have been shocked, their atomic structures distorted in ways that require immense pressure, pressures most often associated with impacts. There are bits of melted rock, microtectites, and fragments that look like they were flung and quenched. There is also a chemical whisper that became famous, a spike in iridium. Iridium is not absent on Earth, but it's relatively rare in Earth's crust compared to many meteorites. Finding a concentrated iridium layer at the boundary, appearing worldwide, was like finding a dusting of starlight in the clay. It didn't, by itself, prove everything, but it was a powerful clue. And as more clues arrived, shocked quartz, spherules, the crater itself, the story gained weight. What's calming in a way is how methodical this is. No single piece of evidence has to carry the whole narrative alone. Science doesn't ask for one perfect smoking gun. It gathers a room full of witnesses. It looks for patterns that repeat in different places and different materials. So imagine the planet in the days and weeks after the impact, not as a neat sequence, but as overlapping waves of consequence. First come the immediate physical waves, earthquakes traveling through the crust, triggered by the shock. The ground shudders far from the impact. In coastal regions, water responds. Huge waves, tsunami-like surges, move across basins, reshaping shorelines, tearing up sediments, leaving chaotic deposits in some places. The exact behavior varies with geography, ocean basins, continental shelves, distances, angles, but the concept is simple. When you hit a planet, the planet moves. Then there is fire, but fire in a complicated sense. For years, people imagined a single global firestorm, as if the whole surface of Earth ignited at once. The real picture is more nuanced and still discussed. Yet, it's very plausible that large regions experienced widespread burning. One reason is what falls back from the sky. Some ejecta re-enters the atmosphere at high speed and heats the air by friction, like countless shooting stars arriving all at once. That re-entry heating can be intense enough to ignite dry vegetation in some areas, especially where conditions are already flammable. So you can imagine patches of the world catching fire, forests, grasslands, peatlands, creating soot that rises into the air. You can imagine smoke spreading, joining the dust and aerosols already forming. And then, slowly but inexorably, the light begins to fail. This is where the event becomes less like a single catastrophe and more like an environmental trap, a snare that tightens over time. Dust, ash, sulfate aerosols, soot, all of these can reduce sunlight. Not forever, but long enough to matter. The impact site likely contained sulfur-rich rocks, meaning that the collision may have injected large amounts of sulfur compounds into the stratosphere, forming reflective sulfate aerosols, similar in principle to what large volcanic eruptions can produce, only potentially far larger. These aerosols and fine particles can spread globally, circling the planet on high winds, lingering above weather systems. They don't just dim the sun like a cloudy day, they can change the balance of heat. Less solar energy reaches the surface, temperatures drop, and the rhythm of seasons becomes strange. In a soothing way, you can think of it like a lamp turning down in a room where everything depends on that lamp. The room doesn't explode, it simply becomes harder to live in. Plants rely on light. Phytoplankton in the ocean rely on light. When light drops sharply, photosynthesis slows. When photosynthesis slows, the foundation of food webs weakens. It's easy to say that and move on, but if you pause on it, gently, quietly, it becomes clear why this mechanism is so devastating. The most resilient systems on Earth are those with deep, continuous energy input. Sunlight is the ultimate income for most life. It's the paycheck that arrives every day. When the paycheck stops, the savings begin to run out. In the ocean, this can happen quickly. Plankton populations can crash, and when plankton crash, everything that feeds on them feels it. Small zooplankton, then small fish, then larger fish, then predators. The ocean doesn't go empty, but it can simplify, lose diversity, and struggle to sustain large bodies that require steady feeding. On land, herbivores suffer as vegetation growth slows and as leaves become scarce or less nutritious. Then carnivores suffer because prey becomes scarce. Scavengers can benefit briefly from widespread death, but even scavengers cannot live on a one-time feast forever. Eventually, the whole system tightens. Meanwhile, the atmosphere itself is changing. If sulfur aerosols are abundant, they can contribute to cooling. If soot is abundant, it can absorb and scatter light in ways that also reduce sunlight at the surface. Dust can fall out more quickly than aerosols, but in the early period, it adds to the dimming. There may also be acid rain. When sulfur compounds and nitrogen oxides interact with water in the atmosphere, they can form acids that fall with rain, stressing plants and freshwater systems. Again, this isn't a simple on/off switch. It varies by region, by rainfall patterns, by how much chemistry is in the sky. But it's one more pressure layered onto organisms already dealing with cold and darkness. And above the clouds, high in the atmosphere, there may be changes to ozone chemistry as well. Another factor that can affect life, especially once the dust begins to clear and sunlight returns in a harsher, more ultraviolet-rich form than before. This is one of the most haunting aspects of the sequence. The crisis may come in phases. First, darkness and cold. Then, as the sky clears, a different kind of stress. A sun that returns to ecosystems that are already damaged, already thinned, already struggling. Now, in a sleep documentary, it's tempting to make this dramatic. Constant chaos, constant catastrophe. But let's keep it gentle and realistic. Earth is large. Effects are uneven. Some places are hit harder, some are buffered. Freshwater environments can sometimes be more resilient than open oceans because they're fed by local nutrients and can be partly sheltered. Burrowing animals can hide from heat and from immediate fallout. Seed banks, seeds resting in soil, can wait out harsh periods. Small animals with flexible diets can switch foods. Creatures that can enter dormancy or that reproduce quickly can rebound faster. So the story is not simply everything dies. The story is the rules of survival abruptly change. If you were to watch the weeks after the impact, as if you could hover quietly above the planet, you might notice an eerie reduction in the usual signals of life. Fewer green bursts of growth, fewer blooms, less plankton productivity in sunlit waters, migrations disrupted, breeding cycles broken, and the temperature changes would be felt in the bones of the world. Frost in places that rarely see it, snow in unusual seasons, cold snaps that last longer than expected, the kind of chill that changes what plants can do, what insects can do, what reptiles can do. Because reptiles, including non-avian dinosaurs, are deeply influenced by temperature. Their physiology, whatever specific forms it took, would have faced challenges in a world that suddenly became colder and darker. Large body size can help retain heat, but it also demands food, and food becomes scarce. So we begin to see why certain groups are especially vulnerable. Large-bodied animals, specialized feeders, organisms with slow reproduction, creatures tightly linked to complex food webs. The impact doesn't need to directly kill every dinosaur to end the age of dinosaurs. It only needs to break the networks that keep large populations stable. And that's what a prolonged disruption of sunlight can do. Now let's return for a moment to the physical evidence again, because it's part of what makes this story feel grounded rather than mythic. Around the world, in rocks that formed at the boundary, geologists find a kind of event layer, sediments that look abrupt, as if something arrived quickly and then settled. In marine sediments, the types of microfossils change dramatically. Certain plankton groups decline sharply. Reef ecosystems shift. On land, pollen and spores can show a fern spike in some places, a pattern where ferns, which can be good at colonizing disturbed ground, briefly become unusually common, like the first green breath after devastation. In some sites, there are chaotic deposits consistent with powerful water movement. In others, there are layers rich in soot or charcoal, signals of burning. In still others, there are glassy spherules, tiny beads formed from melted rock. These are not stories invented to entertain. They are physical traces, quiet and stubborn, preserved by geology. And the Chicxulub crater itself, found through geophysical surveys, drilling, and careful interpretation, ties the whole narrative to a place. A real location on Earth with shocked rocks, melt layers, and the signature of a massive impact at the right time. Now, imagine, gently, the sequence as if it were unfolding in slow motion. The impact. Seconds. The shock and immediate blast zone. Minutes. The ejector plume. Minutes to hours. The return of debris, the ignition of fires in some regions. Hours to days. The spread of aerosols, soot, and dust. Days to weeks. The deepest darkness and cold. Weeks to months. The longer recovery and lingering climate disruption. Years. And then, beyond the immediate years, the ecosystem recovery that takes much, much longer, because rebuilding complexity is slow. Life can persist, but returning to stable, diverse systems takes time. Of course, not every detail is settled with absolute certainty. That's part of the honest beauty of this field. It's a detective story still being refined. Scientists continue to debate the precise duration and intensity of the impact winter. They refine models of how much sulfur entered the stratosphere, how much soot was produced, how quickly dust fell out, how ocean circulation responded, how regional climates diverged. They drill cores from the crater and boundary sites to better understand the minutes to hours deposits immediately after impact. They compare fossil records across continents to see how extinction patterns varied. But the core framework remains remarkably sturdy. A large impact happened. It produced global environmental effects, and those effects align closely with the mass extinction at the boundary. So if you're letting this become a calm picture in your mind, you can picture the moment not as a cinematic explosion, but as a turning of the planet's dimmer switch. A world that was bright becomes shadowed. A world that was warm becomes uncertain. A world that was full becomes thinner. And then, eventually, after the sky begins to clear and sunlight returns, the survivors begin to shape what comes next. But in this portion of the story, we linger in the altered light. We imagine days that feel muted, as if the sun is always behind a veil. We imagine colder winds and quieter forests. We imagine seas that look the same on the surface but are changing in their invisible chemistry and in the microscopic lives that sustain everything else. And we remember that the most powerful events on Earth are not always the loudest in the long term. Sometimes the most powerful events are the ones that change the background conditions, light, temperature, food, until life has to reorganize itself. So gently, hold that image. The thin line in the rock, the boundary clay, the quiet evidence of a sky once filled with dust and glass and darkness. A planet turning under a dimmed sun. A world trying to breathe through a season of shadow. In the first hours after the impact, the world doesn't simply end, it moves. It moves in the way a struck bell moves. Vibration traveling outward, not just through air, but through stone. The ground carries the shock. and far from the place where the asteroid hit, landscapes that look peaceful can still shudder. The shaking isn't a single neat tremor. It's a complicated pulse, energy radiating through Earth's crust, reflecting, refracting, and arriving in different places at different times. Along coasts and across ocean basins, water responds. Even if you never saw the impact flash, you might notice the sea behaving strangely, pulling back, surging forward, sloshing in enclosed basins, churning up sediments that have lain undisturbed for ages. In some places, it's likely that enormous waves travelled outward, tsunami-like in scale, racing over deep water and then rising into shallower shelves with sudden force. Where they met land, they would have torn at shorelines, carried debris inland, and then retreated, leaving behind chaotic deposits, mixed layers of sand, shells, broken fragments, the kind of messy geology that says, very quietly, something fast and powerful happened here. And then there is the sky, which is no longer the same sky. For a while, the atmosphere becomes crowded with things that don't belong in air, dust so fine it behaves like smoke, sulfate aerosols formed from sulfur-rich material, and soot from burning landscapes. Some of this arrives immediately, some accumulates over days, some lingers longer in higher layers of the atmosphere where rain cannot easily wash it away. The sun still rises, but it rises into a world with a veil drawn across it. At first, the most dramatic scenes would have been regional, the immediate blast zone, the roaring winds, the heat. But the longer, quieter danger comes from the slow dimming, because dimming is not dramatic, and yet it reaches everywhere. There's a certain kind of hush that comes when sunlight weakens. You can feel it even in a modern winter when clouds stay for days. How plants seem to pause, how animals conserve energy, how the landscape feels muted. Now imagine that hush spreading across seasons, arriving at a world whose ecosystems are built on steady light. Photosynthesis doesn't stop everywhere at once, and it doesn't stop equally, but it falters. And when it falters, life begins to spend what it has rather than what it earns. On land, plants can survive for a while on stored energy. Some drop leaves, some slow their growth, some die back to roots. Seeds wait, spores wait. Ferns, so good at taking advantage of disturbed ground, may spread quickly in certain places once conditions allow even a little light again, like the first green breath after a burn. But the big leafy productive world of the late Cretaceous doesn't keep producing the way it did. And that means the herbivores, especially the large ones, begin to face a problem that size cannot solve. Large bodies are wonderful in stable ecosystems. They store heat, they dominate space, they can travel far. But large bodies are expensive. They need food, and not just occasionally. They need it reliably. The first phase might have looked deceptively normal in some areas. A forest can still look like a forest even as its growth slows. A river valley can still hold greenery even as new shoots become scarce. Animals can still move, still drink, still search. But as days become weeks and weeks become months, the math of survival becomes harder. The landscape offers fewer calories. The young struggle. The weak fall behind. The great herds thin. And when herbivores thin, the predators follow, because predators don't just need prey, they need enough prey. A carnivore can survive a while on scavenging if many animals die quickly, and in the early period after the impact, there may have been grim abundance of carcasses. But scavenging is a brief gift. It fades, And then the hunters face emptier plains. The oceans, too, feel the dimming in an especially sharp way, because the ocean's vastness is built on something small, plankton that live near the surface where sunlight reaches. When light is reduced, plankton productivity declines, and the effects cascade, first through tiny grazers, then to fish, then upward to larger predators. Some marine food webs can shift toward detritus, feeding on dead organic matter sinking from above. But detritus is also a finite resource when new production is weak. The sea doesn't become lifeless, but it can become simplified, unstable, unfamiliar. There is also chemistry. When the impact injects sulfur and other compounds high into the atmosphere, rain can become more acidic in some regions, stressing plants and freshwater systems. Dust and aerosols can cool the surface, altering rainfall patterns and making droughts harsher in some places, floods more frequent in others. The climate doesn't just get colder, it becomes strange. Seasons don't behave the way organisms expect. Timing, so important for nesting, flowering, migration, slips out of sync. And within that strangeness, the world begins to choose, without intention, who is more likely to endure. Survival, in such moments, often favors the small, the hidden, and the flexible. An animal that can burrow has an advantage. Underground, temperature swings are buffered, smoke and fallout are reduced. A creature that can eat many things, seeds, insects, carrion, roots, has options when its favorite food disappears. An animal that reproduces quickly can rebuild numbers faster after a crash. A creature that lives near fresh water may find more stable refuge than one dependent on wide-open marine food webs. You can imagine, if you like, a quiet set of refuges scattered across the planet. River valleys sheltered by geography, lakes and wetlands where some plants persist, coastal pockets where currents keep conditions a little less extreme, forested slopes where snow and frost are less punishing than on open plains. These are not safe places exactly, but they are places where life can endure long enough to see the world brighten again. And above all, you can imagine life learning to live on leftovers. There is a phase in major ecological disruption where decomposers and scavengers can dominate the flow of energy. Fungi, bacteria, detritus feeders, organisms that thrive on dead matter may become unusually important. It's not a pleasant image, but it is a natural one. When the living world shrinks, the recycling world grows, and it keeps nutrients moving until productivity returns. In that dim, cold period, many groups vanish from their familiar roles. Some disappear entirely. In the sea, whole lineages that once seemed eternal are cut away. On land, the great non-avian dinosaurs, so successful for so long, are among the most conspicuous losses, not necessarily because the impact targeted them, but because the kind of world that follows no longer reliably supports their way of being. And yet something quietly profound happens. One branch of dinosaur life continues. Birds, avian dinosaurs, survive. Not all birds, not everywhere, but enough. Small bodies, flexible diets, the ability to shelter, to reproduce, to move quickly. These traits matter when the planet becomes unstable. Mammals, too, persist. Again, not as the rulers of the world, not yet, but as small, adaptable creatures already accustomed to living in the margins. In a sense, they are pre-adapted to hardship because they have never had the luxury of dominating vast landscapes in daylight the way the big dinosaurs did. They know the shadows. They know the burrows. They know opportunism. The crisis doesn't end suddenly. It eases. Dust falls out faster than aerosols, so over time, the sky begins to clear. Light returns in stages. Temperatures slowly rebound. But the world that returns is not the same world that left. It's thinner. Many niches are empty. Many complex interactions, predator-prey balances, plant-pollinator networks, reef communities have been disrupted. This is where recovery begins, and recovery is not a sprint. It's a long, slow assembling, like rebuilding a city after a storm, except the builders are every surviving species, and the tools are mutation, selection, migration, and time. At first, ecosystems are simpler. You might find landscapes dominated by hardy pioneer plants, ferns, shrubs, opportunistic flowering plants, organisms that can colonize quickly when competition is reduced. Forests may take time to return in full complexity, and in some regions, the early post-impact world might look more open, more patchy, more raw. Animals that survive begin to explore the quiet spaces left behind. Insects diversify and shift, following plants. Small reptiles and amphibians persist in wetlands and forests. Crocodilians and turtles often endure, in part because their lifestyles can be remarkably resilient. Semi-aquatic refugees, flexible diets, slow metabolisms in some contexts. Fish in freshwater systems can rebound faster than those tied to open ocean plankton cycles. Birds begin to radiate into new roles. Some become ground foragers. Some move into shoreline niches. Some become seed eaters and insect hunters in changing forests. Their ability to fly isn't just movement, it's escape, scouting, the ability to search wider areas for scarce resources. Mammals begin to do something that would have been harder before. They begin to experiment with size and lifestyle. Not overnight, not in a neat line, but gradually, generation by generation, as the constraints shift. With fewer giant herbivores dominating plant biomass and fewer giant predators controlling large prey dynamics, there is room. Room for medium-sized animals, room for new feeding strategies, room for the slow emergence of larger mammals over time. But keep the scale gentle in your mind. Even after the catastrophe, the world is still full of life. It's just reweighted. The loudest voices have been silenced, and quieter voices can now be heard. In the oceans, recovery follows its own rhythm. Plankton communities change. Some groups that once dominated never return in the same form. New groups take their place. The chemistry of the oceans, affected by temperature, carbon cycles, nutrient availability, slowly stabilizes. Coral reefs and reef-like ecosystems eventually reappear, but reef recovery is typically slow after major disruptions, because reefs are complex structures built over long time scales. It's possible to imagine the early Paleogene seas as calmer in one sense, fewer huge marine reptiles slicing through the water, but also more uncertain, as new food web structures settle into place. And as the millions of years pass, the world becomes lush again, but with a different cast. Forests become more familiar to us in outline, increasingly dominated by flowering plants. Grasses will come later in prominence, but the trend toward angiosperm-rich ecosystems continues. Mammals diversify into many lineages: runners, climbers, diggers, early grazers, early predators, each exploring a niche that is now available. Birds become more varied. The planet's soundscape changes, different calls, different rhythms, different patterns of movement. It's one of the quiet paradoxes of mass extinction. It is both loss and reorganization. Not a good thing. There is nothing gentle about the suffering and disappearance. but it is also the opening of evolutionary space. The world becomes a different kind of world. And if you want to hold a calming thought while thinking about that vast transition, it can be this. Life does not return by memory. It returns by possibility. It tries what works. It becomes what the new world allows. Now, as we drift toward the evidence, toward how we know any of this, the story becomes almost tender in its detail because the clues are so small compared with the magnitude of the event. A mass extinction is not written in huge letters across the rock. It's written in thin lines, in subtle chemical changes, in tiny fossils, in layers of sediment that you could scrape with a fingernail. In some places, you can stand before a cliff where the rock is pale and layered, and then there is a thin band, darker, finer, marking the boundary between one age and the next. At Stevens Clint, that boundary is famously visible, a slender seam that separates the last Cretaceous from the first Paleogene, like a quiet pause in a long sentence. There are other sites too, scattered around the world, each one a page in the same book, preserved under different conditions. In Italy, near the town of Gubbio, there is an outcrop at Bottacione Gorge, where boundary layers helped shape the modern impact hypothesis. Researchers like Luis Alvarez and Walter Alvarez became closely associated with the idea that a global iridium spike could point toward an extraterrestrial impact, an idea that was once controversial and is now foundational. The iridium is one of the best-known signals, but it's only one. In boundary layers, scientists look for shocked minerals, quartz, whose internal structure has been altered by immense pressure. They look for tiny glassy spherules, droplets of melted rock that cooled in flight. They look for soot and charcoal in some deposits, signs of widespread burning. They look for sudden changes in pollen and spores, indicating disrupted plant communities. In marine sediments, they look for abrupt turnover in microfossils like foraminifera, tiny shelled organisms that record ocean conditions with exquisite sensitivity. There is also the crater itself, Chicxulub crater, partially buried but detectable through geophysical surveys and confirmed through drilling. The crater is the kind of anchor evidence that turns a pattern into a place. It tells us that something truly enormous happened at roughly the right time, in the right kind of geological setting to produce global atmospheric effects. And then there is timing, how we align the clues. Geologists use multiple methods: radiometric dating of volcanic ash layers, magnetostratigraphy that tracks Earth's changing magnetic field recorded in rocks, biostratigraphy that compares fossil assemblages across regions. No single method is perfect everywhere, but together they allow a strong reconstruction. A sudden boundary, a rapid extinction in many groups, and a global event layer consistent with impact fallout. Even with all this, the details are not finished. They never are. That's part of what makes the story feel alive rather than frozen. One of the long-running questions is how the impact interacted with other stresses already present. The late Cretaceous wasn't a perfectly calm background. In India, the Deccan traps were erupting in huge pulses across a broad span of time, releasing gases that could influence climate and ocean chemistry. Some researchers argue that these eruptions added significant stress before the impact, possibly weakening ecosystems and making them more vulnerable. Others argue that the impact alone can explain most of the extinction pattern, with volcanism as background noise or as a complicating factor rather than a primary driver. There are also ideas about timing, whether some eruptive pulses increased after the impact due to seismic effects, or whether the two phenomena simply overlapped by chance in the same broad window of time. Another question is the precise shape of the impact winter. How dark did it get, and for how long? Was soot the dominant sunlight blocker, or sulfur aerosols, or dust? Different models weigh these factors differently. Some propose a very sharp, deep cold period lasting months to a few years, with longer-term ecological consequences stretching beyond that. Others emphasize that even a relatively brief collapse in photosynthesis can be catastrophic if it happens at the wrong time and across the whole planet. There are also questions about fire. How global was burning? Did re-entering ejecta ignite widespread wildfires, or were fires more regional and patchy, shaped by local climate and vegetation? The presence of soot and charcoal suggests significant burning in many contexts, but translating those signals into a single fire story for the entire planet is complex. And then there are the patterns of survival, which are fascinating precisely because they are uneven. Why did some bird lineages survive while others did not? Why did crocodilians persist so well? How did freshwater systems buffer the crisis compared with open oceans? Which plants recovered first in different regions? And why do some places show strong fern spikes while others don't? In other words, what did refuge look like on a planet that was, in many ways, globally affected? Sometimes the most important answers are subtle: local geography, timing of seasons, availability of sheltered habitats, differences in diet, differences in reproduction, and plain luck. Being in the right place when conditions tipped. And behind all these questions is a deeper scientific humility. The fossil record is not a perfect library. It is a set of surviving pages, and many pages are missing. Some environments preserve fossils beautifully, others erase them. Some organisms fossilize easily, others vanish without leaving much trace. So scientists build the clearest story they can from incomplete evidence, always ready to revise details when new data appears. Still, even with the uncertainties, the overarching picture remains remarkably coherent. A massive impact occurred. It left a crater and global fallout. It injected material into the atmosphere that dimmed sunlight and altered climate. That disruption collapsed photosynthesis and destabilized food webs. The extinction was severe and selective, removing many dominant large-bodied groups on land and causing major turnover in the oceans. The survivors, often smaller, more flexible or more sheltered, rebuilt a new world over millions of years. If you let that settle into your mind in a calm way, it becomes less like a disaster movie and more like a deep-time lesson about dependence. Life depends on light. Life depends on patterns. And when patterns break suddenly, life doesn't argue with the universe. It adapts, or it disappears, or it finds shelter and waits. So when you imagine the boundary layer in the rock, think of it not just as an ending, but as a seam, thin, quiet, and unimaginably important. Above it, the world changes in voice and shape. Below it, the age of giants continues for one last breath. And perhaps the most restful thought in the whole story is this: even the greatest upheavals become, eventually, a layer of stone. The planet absorbs the moment. The oceans keep moving. The continents keep drifting. The sky clears. Seeds sprout. Small creatures step into empty spaces. Forests return. Deep time is patient. It holds catastrophe and recovery in the same gentle hand, and it reminds us, softly, insistently, that the world is always becoming something new.